Hello viewers, here is Dr. Mala Das Sharma. Welcome you to my tiny YouTube channel MALACHEMPHILIC. Today I am going to start video number 128, which is the 67th episode of Chemical Thermodynamics, and the topic of this episode is ideally dilute solution and Henry's law. So let's start. In my last video, I have discussed the characteristics or thermodynamic criteria of ideal solution. And today's topic is ideally dilute solution and Henry's law. So ideally dilute solution, what is that? The solution where solvent obeys Raoult's law but solute obeys Henry's law are ideally dilute solution. Actually, in ideally dilute solution, the solvent mole fraction or solvent concentration is very high. So, mole fraction is almost is equal to 1. That means solute concentration is very, very low. So, solvent molecules are mostly surrounded by solvent molecules and solute molecules are also surrounded by the solvent molecules. That is ideally dilute solution. We will discuss it. Before that, we will discuss Henry's law. So, what is Henry's law? Now, Henry's law states that at equilibrium, that means equilibrium of the vapor phase and the liquid phase. So, at equilibrium, the vapor pressure of the solute I, that means solute component we are denoting by I, above an ideally dilute solution is proportional to the mole fraction of I in the solution. So, what is that expression? Here, the vapor pressure of this solute, that is partial vapor pressure of this solute, that is proportional to, so P solute, this will be proportional to the mole fraction of the solute in the solution. Okay. So, if I make it equal, then vapor pressure must be equal to mole fraction of the solute multiplied by some constant. Here this constant is known as the Henry's constant. It is not is equal to the vapor pressure in the pure state at the same temperature, just like Raoult's law. Here this constant is different. Okay. And this KH is known as the Henry's constant. Now, so we are going to derive now this Henry's equation or Henry's law. So, like Raoult's law, this Henry's law is also applicable for the liquid vapor equilibrium. Actually, Henry's law is for the solution of gas in the liquid, where it is stated that this at equilibrium, the solubility of the gas or this concentration of the gas or this mole fraction of the gas proportional to the vapor pressure of the component above the vapor pressure of the component in the vapor phase above the solution. Okay. So, like Raoult's law, Henry's law is also for the liquid vapor equilibrium. So, liquid, okay, before that I'll write this Henry's law. Henry's law. So, it is liquid vapor equilibrium. Okay. See, we know that chemical potential of the component, say ith component in the liquid state, that is given by the expression mu I liquid state in the standard condition plus RT ln Xi, where Xi is the mole fraction of the component. Here it is ith component in the solution. And the chemical potential of the ith species in the vapor phase, that will be is equal to mu I in the vapor phase under this standard condition plus RT ln partial vapor pressure of the component. Now we know that at equilibrium What is the condition for the phase equilibrium? Chemical potential of the component must be equal in all the phases. So at equilibrium, we can write mu I in the liquid phase must be is equal to mu I, chemical potential of the ith component in the vapor phase. So these two equations we can equate it. That means what can I write? Mu I liquid phase under standard condition plus RT ln xi is equal to mu I in the vapor phase under standard condition plus RT ln pi. So from this equation what can I write? We can write mu I under standard condition of the liquid phase minus, if I bring it here, so mu I vapor phase of standard condition is equal to RT ln partial vapor pressure of the ith component minus RT ln xi. We can write it. Okay. So what we can write then? So our equation is mu, once again I am writing here, mu I L standard condition minus mu I V standard condition is equal to RT ln Pi minus RT ln xi. Right? So what can I write now? I can write like this equation. See, I can write ln Pi minus ln xi, that is equal to mu I liquid state under standard condition minus mu I vapor phase under standard condition divided by RT. Okay. So here I can write ln Pi by xi, that is equal to these things, that is mu I L standard condition minus mu I V standard condition divided by RT. And this, and what can I write? I can write that Pi by xi, that is equal to e to the power mu I liquid phase under standard condition minus mu I vapor phase under standard condition divided by RT, and that is equal to constant, because this is constant, chemical potential in the standard state, R constant, T constant, so this is I am taking KH. So therefore what can I write? I can write Pi by xi is equal to KH, Henry's constant. So Pi is equal to KH into xi, or what can I write? Pi proportional to xi. So this is Henry's law. This is the equation where this proportionality constant is different from Raoult's law. Now, so this is our Henry's law. Vapor pressure of the solute of ideally dilute solution, because here we are considering only ideally dilute solution, that is equal to X solute, mole fraction of the solute, into Henry's constant. Okay. Now look at here. We'll make some discussion here. See, Henry's constant depends on the nature of the solute and that of the solvent. See, when this solute is strongly attracted by the solvent, then KH is smaller, that is Henry's constant is smaller. Try to understand. See, from this equation, I can write it X solute is equal to P solute divided by this KH. I can write it. So at equilibrium, there is some mole fraction of the solute in the solution, and that is equal to vapor pressure of that component divided by Henry's constant. Now, if the interaction is strong, that means solute is strongly attracted by the solvent, then what will happen? Less amount of vapor will form. So this vapor pressure will be less. If this partial vapor pressure is less, that means Henry's constant also should be smaller. So Henry's constant will be smaller than that of the vapor pressure of the pure solute. Okay, it is less. Okay, because this is also less. So Henry's constant will be smaller than the vapor pressure of pure solute. And in the reverse case, if the attraction between the solute solvent is less, that means solvent attraction towards the solute is smaller. In that case, what will happen? If the attraction is smaller, more amount of vapor will form, partial vapor pressure will be more. So this Henry's constant also will be more. So in that case, Henry's constant will be higher than that of the vapor pressure of the pure liquid solute. Okay. Then another discussion depending on the temperature. This Henry's constant depends on the temperature. See, this value of this Henry's constant of the gas dissolved in liquid, it is significantly greater at higher temperature, because at higher temperature gas phase is or vapor phase is favorable. Because vapor phase, why it is favorable? Because entropy increases, disorderness increases. Okay, any system tries to go from the ordered state to disordered state. So what will happen? That higher temperature, entropy of the gas phase is much higher. So mostly that it will go to the vapor phase. That means solute molecules will go to the vapor phase. Okay. Because here the entropy of the liquid phase is less than that of the gas phase. Okay. So when it goes to the vapor phase, so once again we can write, say as I wrote, X solute will be is equal to P, that is vapor pressure of this solute, divided by KH. Okay. Now gas phase is more, that means this vapor pressure is more. So what will happen? This KH, Henry's constant, will be much higher. Now, see, in ideally dilute solution, as I told you that here, 1 minute. Here you see this solvent concentration is almost equal to 1. Concentration in the sense that is the mole fraction, almost is equal to 1. That means solute concentration, let's say here 0.9999. Solute concentration is very low, 0.0001. Okay. So this solute is mostly surrounded by solvent, and most of the solvent also mostly surrounded by solvent. See here it is little bit surrounded by solute molecules like that. So this ideally dilute solution here, this solvent mole fraction is almost close to 1. But this ideally dilute solution are not ideal solution, because here the solvent-solvent and solute-solute interactions are different from that of the solute-solvent interaction. Okay, but as the solute is mostly solvent is mostly surrounded by these solvent molecules only, and its mole fraction is very high. So the solvent in this ideally dilute solution obeys Raoult's law. Okay. Now, here as I told you, these solute molecules are surrounded by the solvent molecules, which is entirely different from the environment of the pure solute molecules. Okay. Here, the solute molecules, as I shown you in that diagram, that it is solute molecules are mostly surrounded by the solvent molecules. So this environment is totally different from the pure solute molecules. Okay. Understood? Thus, the solvent molecule behaves like a slightly modified liquid. Solvent molecules is just like a pure solvent only, because mostly it is surrounded by the solvent molecule. It is just like slightly modified pure solvent. But the solute molecule behaves entirely different from the pure state, unless the solvent and solute molecules are very, very similar. In that case, the solute also obeys Raoult's law. Now, this vapor pressure, already this point I told you, vapor pressure of the solute proportional to the mole fraction in the solution, but the proportionality constant is Henry's constant, which is not equal to the vapor pressure in the pure state at the same temperature. Then, so now coming to the standard state. The standard state of the solute is a fictitious state at same temperature and pressure of solution, in which the solute is pure, but it is experiencing that its molecules are experiencing the same intermolecular forces when it is surrounded by the solvent. Solute molecule is pure, but it is experiencing intermolecular forces as if it is surrounded by the solvent molecules. Okay, so this one. Solute is pure, but it is surrounded by the mostly solvent molecules. So it is experiencing the same intermolecular forces, when surrounded by the solvent molecules. Now, and the solvent standard state is the pure state at the same temperature. Okay, because solvent is mostly surrounded by the solvent molecule. Only here, as I told you, this solvent molecule is little bit surrounded by this solute molecule. So it is almost pure state, slightly modified. So solvent standard state is the pure state at the same temperature and pressure of this solution. So for solvent, this partial vapor pressure is as per Raoult's law. This mole fraction multiplied by the vapor pressure in the pure state at the same temperature. But solute vapor pressure is as per Henry's law, that is vapor pressure is equal to mole fraction multiplied by Henry's constant. Now coming to the vapor pressure composition curve for solute in ideally dilute solution. Let's see the curve. See, this is vapor pressure, this side mole fraction, and this side mole fraction of B is increasing, right? Now, so this side mole fraction of B is 0, that means A is 1. Now we are adding B to this A, that is solvent molecule. So the solutions are forming. These are the different composition of this solution. And if it is ideal, then this is the curve for the mole fraction versus vapor pressure of this solute. And if it is, say, non-ideal and these solute-solvent interactions are less compared to solute-solute or solvent-solvent, then this will be the curve for the solute. Solute-solvent interaction is less in the solution compared to solute-solute or solvent-solvent. But in case of ideally dilute solution, here it is ideally dilute solution, then this curve for this vapor pressure versus mole fraction of the solute will go like this. Okay, straight line. Because this is the proof of Henry's law, Henry's equation. So this is the vapor pressure composition curve for the solute of ideally dilute solution. So ideally dilute solutions are very dilute, where this mole fraction of the solvent is almost equal to 1. So solute concentration is very, very less, and the solute is mostly surrounded by solvent molecules. So its standard state is different from that of the pure state, whereas solvent is mostly surrounded by solvent molecules. So its standard state is same as that of the pure state in the same temperature. Hope you have understood. Thank you.